So good morning, everybody. My name is Jesse, and I am with Exploring by the Seat of Your Pants. For those joining us for the first time, we are all about bringing conservation, adventure, and science into classrooms around the world. And we are particularly excited this February because all month long, we are only celebrating amazing women in science. By month's end, it'll be over 40 hangouts with incredible women from astronomy to zoology and everywhere in between from across the globe. And it's our biggest festival we've ever done during February. And so we appreciate you guys being a part of it so much. It's so important to highlight incredible women in STEM, and so we appreciate you guys being here to be in that festival with us. Right now, we are joined by 7 classes from across North America, so I want to give them a chance to do a bit of a shout out. We've got Miss Stecco's great group in Greenbrier Middle School. Great first time enthusiasm, I love it. We've got Miss Evans, grade 6s in Haines, Oregon. Hi, guys. Who are so loud on their couch because they have a couch in their classroom that they are breaking the mic, and I appreciate it. We've got Miss Williams, grade 4s in San Antonio in Texas. Hi, guys. Hi. The mic's muted. It's not letting me demute it, but I feel your enthusiasm. We've got Mr. Seaburgers, grade 8s in Cambridge, Ontario. Hi, guys. Awesome. We've got Miss Gills, grade 5, 6s, also in Cambridge, Ontario. Hi, guys. Hello. We've got Miss Walters, grade 6s in Cordis, Ontario. Lots of Ontario today. And just joining us, last but not least, we've got Miss Miller's, grade 5s, also in Brampton, Ontario. Hi, guys. You guys are really low pitched. I like it. We could get like a choir going with everyone. I appreciate it. Of course, the reason you guys are all here today is for our speaker. So we are joined live from London, Ontario by Dr. Parshati Patel. She is an astrophysicist at the Centre for Planetary Science and Exploration at the University of Western Ontario. So a really, really cool job. And in addition to studying the cosmos and all its mysteries, she is a really prominent science communicator. She does work all over Ontario, sharing her love of space and the universe with kids. And so we always appreciate having her back. Thanks so much for joining us, Parshati, and take it away.
Thank you so much. Thank you, all the classes, for joining in. I'm really excited. So I have a bit of presentation before we do Q&A. So I'm going to kind of talk to you about what I like about space and what my, what intrigues me on an everyday basis. So I'm going to load in my presentation after I share my screen. And we'll start from here. All right.
You're in.
Awesome. Okay, so today I'm going to talk to you about a stellar detective. And, when I was very young, almost age of what you guys are right now, I always wanted to be a detective. And when people think about a detective, it's generally someone who wants to investigate and solve crimes. When talking about the universe, obviously there's no crime here, but there are tons of mysteries. It's full of mysteries. And what kind of intrigued me when I was young was to solve these mysteries, whether it's in crime or anything else. So for my research, I picked up this really neat mystery of studying these stars that are very, very massive than our sun. And so I'm going to show you guys, kind of take you through the journey of how we go through this cycle of finding a mystery and trying to solve this mystery today. So we're looking at 2 pictures. The top one right here is the Orion Nebula, and the bottom is the Eagle Nebula. These are 2 of my favorite, star-forming regions. So these are regions where you have all the ingredients you need for a star to form. So you have dust, you have gas, you have wind from other stars that is blowing this gas and dust. And you can see in a lot of these regions, you can feel like it's flowing. And that's what the winds, what kind of triggers these star formation. Obviously, there are other things as well that trigger these stars to form in this region. But this is kind of the soup where the stars are going to form from. And I really like to emphasize on these 2 images because even though they look really small in these images, they are very, very large when it looks on the scale. So if you look at this one tiny star where I have my cursor, that's just one speck of star like our sun, and you can see there are so many over here as well as here as well. And when we look at these pictures, so I'm going to kind of zoom in on this Orion Nebula. when we have powerful telescopes that actually point to these regions, we look for these stars that are just forming and try and take pictures of them to see where they are in their stage of life. And we get pictures such as these. You have this one right here with a very dark disk. And then over here, this one has a very long tail. So it probably has wind that's blowing off of this almost newly formed star. And you can see they come in variety of shapes and sizes. They come in variety stages of their life. So what I do like to see is what is going on when these stars are forming. That's kind of the mystery that I like. And if I were to actually take a spaceship and go closer to one of these, it would look something like this. You have a star that is being born right in the center. You have a disk of material, which is right here. You have gas and dust that's going around the star. And sometimes if the material that's around the star is falling onto that star in the center, you get these really straight jets out of the two sides of the stars. And those are very, very interesting to study as well, because they're pushing all this material out of the star plus the disk. Now, what's interesting to see in this one is that even though I can see this really thick disk, I can hardly see the star. I can hardly see the star the way we see our sun. And I'll show you an example of what other pictures Hubble took when it was looking at the Orion Nebula. And you can see they come, they have one jet sometimes they have two, or sometimes they have just a blob of dust and gas that's kind of blowing away. And sometimes you just have, a tiny, tiny disk that's blocking the star and nothing else around it. And so what I really, really wanted to understand was how these stars form while we cannot actually see them. And so if we look at, how it goes from a really, really big region like that of the one right here, Orion Nebula, and it compresses into this star and a disk around it. And that's where the star is born. That's where all the planets in this disk are going to form. So it's kind of a birth of a star. That's what I'm looking at, how it happens, just using the light from those stars. So if we look at different kinds of stars in the universe, obviously there's a whole lot of different sizes of stars. So our sun, even though it looks very big in the sky, it's actually not one of the biggest stars. There's a whole variety. So if you look at from M through O here, these are all to scale. So if you were to put our sun, which is a G-type star, right here, this is how small the M-type star would be and how big this O-type star would be, okay? And the more bigger they are, the more massive they are. Obviously, the bigger mass means bigger temperature. That also means they have a lot more fuel. And so they burn through their, basic life cycle very, very fast. So the more massive stars, they live fast and they die fast. And that's what makes them very interesting, because stars like our sun, they're around for a long time. You can see, you can go around and take pictures and you can see a lot of them in different stages of life. But when you look at these massive stars, they are born really fast. They go through their life cycle really fast, and then they die really fast. So it's very interesting to see how the more mass it has, the faster it goes through its life. And I've just noted the kinds of temperatures on the surface you would find of these stars. So if you look at our sun, it's around 6,000 degrees. But if you look at something that's B or O-type star, can go to 30, 40, 50,000 degrees on the surface. And this is just on the surface. So they're really, really, really hot stars. And they can, their mass can go up to 60 times the mass of our sun. So if you put in 60 suns in one bag, you would get something like an O-type star. So they are really big, they have really high temperatures. And what makes it very interesting is they are born and they live and they die faster than any of these smaller stars that you can see on the slide here. Okay. And so obviously I found my mystery. I really wanted to learn how these massive stars were forming. And obviously, as I showed you before, they were covered in dust and gas around them. So I could not really see them. So I cannot just go ahead and take a picture and be like, all right, this is what's happening and this is how it's forming. I have to try to understand what is happening closer to the star without actually being able to see it. So that was my mystery. I finally found a mystery that I really was interested in learning more about and trying to solve it. So back to this picture again, I just wanted to emphasize that when it also depends on where you're looking at it from. So if I'm looking at it from right how I have the image, obviously I can see a bit of star, but not a lot. But if I were to see it from a different angle, so if I were to go on the top and look at it, I would be able to see the sun. But if I were to go, let's say, a little bit between the top and the middle, I won't really be able to see much. So it obviously depends on where you're looking the star at from. And so I wanted to kind of look at the star from the angle that we are currently looking at because it's blocking most of the star. And so I just want to use the light to study it. And the way we would kind of, if I were to cut this previous image into half, this is how it would look like if I were to be able to do that, where you have a star that's forming right in the center here, okay? And you have a lot of this dust and gas here. And you can imagine these stars, because they're more massive, they're also very, very high in temperature. And so when they're high in temperature, the dust basically evaporates very close to the star. And so all you get is gas around it. So it's very interesting to see where all this material actually lies. All right, so what do I do next to try to solve my mysteries? Actually look for data to see if anyone has actually already looked at these stars, and then also if I need my own personal data from big telescopes. And so for my personal research, I use observations from the Canada-France-Hawaii telescope. This is a telescope in Hawaii that, I was able to get a chance to take images and the light from these stars that I really wanted to study. And what it would really look like is something like this. So this is obviously not my data, but this is something to show you guys. If you were to stretch the light that you would get from these stars, you start seeing these dark lines. And those are the ones that I'm really interested. Now, the next image that I'm going to show you guys, it's a little complicated image, but I really want you guys to only concentrate on the blue lines, okay? So now that I have the data, I'm going to process it. And the way I do it, it's going to look something like this. So don't worry about what the graphs are saying. Just concentrate on this blue line right here, okay? So if I extend the light that I got, I would show all these spikes in my data. So the biggest spike is right here, and there are some more right here. All of these spikes actually tell me a bit about what kind of material is present in the disk around the star. So this particular one tells me there is hydrogen. This one tells me there is oxygen, iron. So all of these different elements that we see here on Earth, I'm able to see them in the material around the star. So now I have this data, I take this data, but then I need to do something with it, right? Trying to solve my mystery. What am I trying to learn? So in order to do that, I'm now developing a theory. What can I learn from the observations that I have and what I'm seeing using images? In order to do that, I basically create a star and a disk around it in my computer. So I generate a disk and a star, just like as you can see in this particular image right here. This is an actual image of the star and the disk that we have generated in our computer. And what we do is we basically take what we have from our observations and take what we have from our computer models and compare them together to see, is my understanding of the star and the disk correct? And basically using that comparison, I can say whether or not what that star is doing at that particular point in time, the time that I got my data. And so if I have a sequence of data over years, I can see the changes that happen in the disk as well as around the star. And that allows me to tell the world what that particular star is actually doing. And so, once we have that theory, we obviously go out and look for more of these stars, and the cycle kind of keeps going. So now when I have more of these stars, I have more mystery. Are all of these stars acting the same, or is there any difference between them? And so then that cycle kind of starts all over again, where I then go look for data, obtain more data, process it, develop a theory, do modeling on my computer, and then test the theory again. So this circle keeps going until you run out of mysteries. And luckily, in our universe, we will never run out of mysteries, and that kind of keeps me excited about studying stars and universe in general. So I'm going to stop right there, and I will be open to take your questions.
Awesome. Thank you so much, Dr. Patel. That was great. So let's start with Ms. Stecco's class. If you guys have a question, come on up to the computer.
Alex. Okay, Rana, do you want to ask a question? Okay, come up to the computer, okay? Go up and what's your lunch, your sweetie? Okay, can they hear us?
Yep.
Kneel down a little, make sure you can see. Okay, ask your question, Rana.
Was this your child passion to be an astrophysicist?
So it actually started when I was 12 years old, when I visited my planetarium in a nearby city. I got really intrigued about what stars and planets and things were, but I wasn't keen on being an astrophysicist until I was gifted a telescope. And the first time I saw Saturn and Moon and Jupiter through my own telescope, I was like, this would be an awesome job to just, look at the night sky and study all these different objects that exist. So that's when I was 14 years old, and that's when I decided that this is what I'm going to do with my life.
Awesome. Thank you so much. All right, Miss Evans' class, if you guys have a question.
Okay, Ashlyn, go.
How long did it take you to finish your degrees and schooling to be an astrophysicist?
Okay, really good question. So after my grade 12, I did 4 years of bachelor's, 2 years of master's, and then 4 years of Ph.D. So that's total 10 years of schooling after grade 12.
So you're done now? Do you have to do any more schooling ever, or are you like firmly in?
I'm done for now.
Take a break for a while, but yes, good question. All right, so Miss Williams' class, if you guys have a question, come on up. You might need to demute your own mic. I don't know why it's not letting me, but just little microphone symbol top of your screen, and I'll let you know when you're good to go. Yep, you're good.
Hi, my name is Evan, and well, how do you know the sun is one of the smallest stars in our
So sun is not the smallest, but it's one of the smallest, and that's because we are actually looking around in the universe, looking at these different stars that exist, and we can measure their size, their distances, where they exist, and things like that. And that allows us to say there are particular categories or particular sizes of the stars that we can find. And so we put them in these different categories that I showed you guys, like M through O. So yeah, initially used to be OAB, OC, OBC, or things like that. And then it was rearranged the moment they found, the M stars are actually the smallest one and the O stars are actually the biggest one. So they rearranged the scale to make it smallest to biggest. Yeah.
Maybe they could make it really simple for people and just name them like the Starbucks cup sizes, like Venti and Grande. Now, this might be too complicated to answer. How do, when we're measuring stars, how do you measure a star that's like many light years away? Is there a way to explain that?
Good point. So there are different ways depending on how far they are. So for example, if their star is very close to us, then what we're able to do is, let's say in January, we measured a star from here. I'm going to try and see if I have something that I could use to explain that. All right, so let's use this circle as something that's our orbit around the sun. If we are on this side and I'm measuring where the star is, I have a certain position for it. Let's say behind me, you can see this particular lamp. And then I move 6 months later, so the Earth is right here, and now you're trying to measure me. I'm a little bit away from that lamp, right? So that allows me to measure what's that difference between my head right here and then my head right here. And because we know the distance between Earth and the sun, we're actually able to use simple triangle law to figure out how far they are, okay? And then obviously, depending on how far they are, we're able to then deduce a lot of different things like what the mass is, what the radius is, the amount of light we're getting, things like that.
This explains why you need 10 years of school after high school. This is perfect.
Yes.
All right, Seaburger, if you guys have a question, again, for some reason you have to demute your own mic. Apologies for that, but you're good to go.
Did you ever consider working for NASA?
Oh, good question. I did when I was young. When I was doing my research, obviously I used Canadian telescopes and Canadian, I guess, observatories and facilities that are available here. So I did consider at one point, but right now I'm happy kind of where I am. And you know, I do get to work with a lot of CSA and NASA agencies, but we're staying in Canada for now.
Okay. For what it's worth, you're still young. Would you, if the opportunity arose maybe down the road, I know you love your job, would you consider that? Other gigs?
Yeah. Absolutely.
We won't share it with your boss. We'll keep it secret. All right. Miss Gill's class, you guys have a question? Go right ahead.
Did they say?
Yep.
Yep.
Okay.
Okay. What are some of the challenges you had to overcome to get to this place in your career?
Great
Oh,
question.
wow. Lovely question. So I'm originally from India. I moved here to study astronomy. So I think my first kind of struggle was, you know, the day one when I arrived in class here, I was very worried if I will understand the language, if I speak the language right. So even though it wasn't more of a scientific hurdle, it was more of, I guess, a personal hurdle when I started here. I did study in an English medium school, so I did have a good background to speak English when I got here. But that was kind of my first hurdle. The second one was actually something that, you know, I would advise a lot of the people who would want to go into this field was that I had to learn coding. And I never actually thought that's something that I would be doing with my life, is actually a lot of the time is spent on a computer, you know, creating these models in a computer. And so I realized in my third year of my undergrad that I did not know how to code. And so I spent my entire summer learning how to code. And so I think that was kind of my first scientific hurdle, where I was so lost in the classes that I decided that I should take 4 months off and just concentrate on learning languages that I will be using. I think once I got into grad school, the hurdle is actually trying to not waver off your topic that you really have chosen, because there are so many exciting things you could be researching on that you were like, oh, maybe I should have done this and maybe I should have done that. So trying to keep yourself focused into this, trying to solve this one particular mystery rather than fanning yourself out in like 10 different things and not, you know, being able to finish things on time. I think that was my second hurdle, is trying to keep my focus towards finishing what I have started.
Outstanding. We've been getting some really thoughtful questions today, so thanks to all the students for that. It's been wonderful. And worth noting too, Parshati, so as a science communicator now, even though you did focus so heavily on one thing, you get to talk about a wide array of topics, which is really nice.
Yeah, it's definitely something that I learned in my grad school, is to kind of also expand at the same, because you're so focused in researching this one particular topic, it's also a good idea to actually step back and look where your particular research kind of fits into this puzzle of the universe. So I'm very lucky on an everyday basis I get to talk about everything in space.
Nice. All right, Miss Walchuk's class, if you guys have a question.
Since Saturn has rings kind of, or since the star and disk has like a ring, kind of like Saturn, do they have any relationship?
Yes and no. Yes, because they're also disks around something. They are material that are floating around another object. So it is, in a scientific term, would still be called a disk. No, in a way, because the way the disk is formed for around a star is all the material that is trying to rush into the center. And at one point when the star basically ignites and is born, you have all this material still floating around it. Eventually, that's where all these planets form from. And for Saturn, this is all the material that's kind of left over, but at the same time, currently being replenished by the moons that exist in the rings of Saturn. So that's why yes and no. There are two different kinds of rings, but kind of their formation, the laws are same, the reason why they form. So yeah.
Before we go on to our last of the first round of questions, so Saturn is the jewel of the solar system, but Parshati, can you tell us about other planets in our solar system that might have rings?
Yeah, so actually all gas giants have rings. So Jupiter has a ring. It's really hard to see because the planet is really big and the ring is really thin. Uranus has rings. If you see it on the sides in some of the pictures, if you Google, you'll be able to see the rings of that planet. And then Neptune also has rings. So, you know, all giant planets, Jupiter, Saturn, Uranus, and Neptune, all of them have rings.
Awesome. Thank you so much. All right, and then Miss Miller's class, come on up. Yeah, and you just need to demute your mic too. Don't know why, but.
Because we're on an iPad. Okay, Spencer.
What would happen if the sun were to burn out?
We do know that that's not going to happen for a while. Thankfully to all the scientists who study stars like our sun, we have still around 4 billion years before it's going to start to swell up, which is going to be bad because at that point Earth is not going to be a good place to be living. And it's going to start to pulsate. It's going to shed off all its, outer layers. It's going to go boom. And at that point, obviously, planets may or may not exist depending on, whether it takes that final phase well or not. We, at that point, would definitely have to move somewhere else if we exist in a few billion years.
Long time. Worth noting that the Earth, it's as long as the Earth has been around, that long again till the sun becomes a real problem for us. But it will become a real problem for us when that happens.
Yeah.
Very scary problem. All right, let's do a whole other round of questions, guys. So let's start again with Miss Stecco's class. You guys have one? Come on.
No, not Verona.
Everybody's got a question.
There you are. Say hi. Hi.
Do you know what type of energy is created when a star is born?
The light that you see. Obviously, there are different kinds of energy depending on what you're looking at. So you have the light that you see from it. You have the energy that's propagating in terms of the material that is being expelled. And then obviously you have energy that's being generated on the surface. So if you look at the sun, you have a lot of material that is being brought up. So that's a different kind of energy. You have the radiation, which is the light and the heat and the warmth that you feel. So depending on the kind of star that is being born, that changes as well. So most massive stars radiate a lot of more energy than what a star like our sun or something that's smaller than that would radiate. So we as humans would certainly see light, and if we were close by, you would also feel the warmth, hotness or the heat from the star.
Okay. And Parshati, just to follow up on that really quickly, how much energy is the sun producing here? Just even our sun, what are we talking about? It's hard to put it in figures, but a lot.
A lot is a good word. I generally don't keep numbers in the top of my head just because it's a really, really big, huge number.
Yeah, like billions of nuclear bombs going off every second in the heart of the sun for 4.5 billion years. It's quite incredible.
4 more billion years or so.
Cool. All right, Miss Evans' class.
Okay.
Come on, guys.
What's the furthest star from us
That you studied.
that you could study?
Okay.
Oh, that you could. So we are our observable universe. So the universe that we can see is as far as 13.5 billion years. Light years in distance. So 1 light year is the amount of light light travels over a year. So if I am here on Earth, light from the sun takes around 8 minutes to get here. The light from Earth to the moon takes around 1.2 seconds, okay, to get there. So you can imagine if you continue on that route, the the distance that the light from the sun would take 1 year, that is considered as a distance because the light travels at a constant speed. And so if we were to look back, we can look at the stars as far as the universe has kind of passed that light from its origin to us, and that is around 13 billion years. And that's how far we can see in terms of galaxies and stars. Obviously, you need better and better cameras if you want to take pictures, but we do take pictures of these galaxies that are further and further away. And as years go by, every year you are seeing something that the light had originated, that many years ago. So it's a pretty interesting concept. It's a very hard concept to get your head around, but it's billions of years in past is where you can see the stars and the galaxies.
Super cool. So a telescope's like a time machine. We can literally see things as they were millions or billions of years ago. Those stars might be dead by now. They might have exploded a million years ago, and we won't know that because the light telling us that won't arrive for a long time to come.
Yeah. One of the examples that I would want to just point out is the closest star is 4 light years away. So when we look at that star, that light has actually been emitted 4 years ago and has just reached us, and that's when we are seeing. If, as Jesse mentioned, if something blows up, so if that star is going to, go supernova, we would see it 4 years later. So that's kind of an interesting, the light would take 4 years to get to us.
Super cool. All right, Mr. Seeberger's class, come on up, guys, and go right ahead. Yep, you're good. Whenever you're ready.
What kind of work do you currently do?
So my work, so I'm now a full-time science communicator and educator. So my work involves actually developing a lot of these workshops where, we take these activities and presentations into classroom based on the curriculum. Well, I work here in Ontario, so based on Ontario curriculum. I do a lot of public events. I do a lot of these kinds of events where I talk to students and I talk to public about how awesome space is, but at the same time, why all of us should be really curious about it. And at the same time, I've recently started working towards studying how the program that we have currently is actually impacting people. So I'm kind of gearing also towards education in, research in education field. So it's a lot of different things that I'm doing at the same time, but that's kind of what I love about my job.
Nice. All right, Miss Gill's class.
Hey, Beth. We're so dedicated, we stayed in for recess for this.
Awesome.
Go ahead, Beth.
What does it feel like to make new discoveries about stars?
Oh, the excitement is great when we actually end up with it, but the time to get there is this hard struggle. It's a lot of research. It's a lot of failures from which we learn a lot. And then eventually, when we actually find something that no one ever has come up with, no one has ever figured it out, it's the best feeling ever. There is 4 years of, at least for my PhD to kind of get there. But when I did get there, it was the best feeling ever. It's like something excited that I'm still excited to share with people, and something that I always want people to know about, but because that was something people did not know about it before. So it's a pretty interesting feeling.
Outstanding. All right, Miss Walchuk's class. You guys have another question?
The letters that were used to label the different sizes of stars, do they stand for anything?
No. So originally, when they were trying to decipher the stars from each other, they had labeled it based on the kind of, those lines that I showed you guys, the spikes. So they were trying to put them in bins of certain A, B, C, D, E, F, G, and they figured out that some of these stars, when they try to put them in the bins based on their mass and their size, they figured out that some of them could be clumped together. And then if you rearrange them, they just turned out this weird thing that goes from M to O. So initially it would have been A, B, C, D, but once we figured out that there were some of them that were very similar to each other and you can basically put them in the same bin, we changed the wording around. And so now M to O, which is very hard to remember.
All right, let's take a second last question for Miss Miller's class. Come on up, guys. And I love that every class, like so many kids put up their hands every time. Like you guys are the best groups today ever. Love it.
Where are these type of stars located? Like where would they be?
Where do you find the type O stars? So the massive stars are actually very common, and in the pictures I showed you guys for the star forming regions, the stars that you can really see mostly are these big O or B type stars. That's because they're really big, they shine really bright, they basically have these really high energetic winds, and so they blow things away, and you're able to actually just see those instead of the tiny bits of stars. But they exist everywhere. Every star forming region will have, its spread of the sizes of stars, but the O type stars are the ones that you can easily see, O and B type stars, because they're very similar in size. Yeah.
Awesome. And we would typically end up there, but I really want to reward the fact that Ms. Gill's class stayed in for recess. So if you guys have another question, go for it, guys.
Who's our third one? Okay, Lucas, come on up. Oops.
How is studying physics in space different from learning everyday physics on Earth?
It's actually very, very similar. The laws of physics stay the same whether you're on Earth or you are on a star or you are on the other side of the universe, which is the coolest part about physics. So, if you're studying a physics law right here on Earth, you most definitely can apply it other places in the universe as well. So when I did my undergrad, I did my undergraduate in physics and astronomy because I really wanted to learn all the physics that I could and then use that and apply to stars. So if you like physics and math, this could be your field.
Awesome. Dr. Patel, before we wrap up, because we've been getting, again, every time we ask a class a question, 10 hands go up. Is there a place where students can learn more about the work that you're doing? Can they get in touch with you? Can they get in touch with Center for Planetary Science and Exploration? Where can we guide people to learn more?
Yeah, definitely. So I do have my personal website, parshatipatel.com, where I do have my research listed, but I also have a contact form. So you guys can email me if you have more questions. I'll be more than happy to answer that. And your teachers might also be able to reach me through Twitter or Instagram. I'm Parshati Patel on Twitter and spacegeek.parsh on Instagram.
Awesome. And I will pass along those to all our classes as well, so you guys can get that directly from me when we're done. All right, guys, this was great. Again, I really want to say to all the classes, this is some of the most thoughtful, amazing questions that we've ever had for any Hangout, especially for physics, which can throw off a lot of classes. So I appreciate you guys so much. You prepared so wonderfully, and it's awesome. So what we do at the end of every Hangout, boys and girls, is I'm going to demute every class's microphones. And if you guys could join me in saying a huge thank you to Dr. Patel for joining us today. You guys are all demuted. I can see why you became a science communicator, Dr. Patel. This is, yeah, awesome.
Thank you so much.
Yeah, this is great, guys. Thanks so much for joining us. We look forward to having you back soon. Thanks for being a part of our February festivities highlighting women in STEM. It's so great. And whether you want to see Parshati again, go to our website, come to our other Hangouts with her and other astronomy of all kinds. We do astronomy Hangouts year-round. We look forward to having you back. And for now,